Are you still craving more science?
Yeah.
Are you craving more enlightenment?
Yeah.
Are you get tired of listening to me?
Yeah.
Well, Tom, you're going to have to listen to me anyways. All right. So, in the middle and high school, we did a very data-intensive look at the solar system. In the elementary school, you also looked at the solar system and organization of the solar system. All right, and the conclusion you come to is that you can, on the basis of data, come up with an organization and a classification of the solar system. All right, I'm here to tell you, give you the full story from my scientific perspective, but I will note, as I said in the last session, if you disagree with me, good. I love it when people disagree with me, as long as you can justify your disagreement with data and evidence, and not just, oh, somebody said this. Okay? So, I will give you my opinion and my perspective on it, and you can you can agree or disagree as you like. All right, so the title of this talk, and I realize I've now been giving this for 10 years now, so this is 3 years before we kicked Pluto out of the solar system officially. We're talking about, it's not your parents' solar system. It's a new understanding of the solar system, okay? And I actually have to turn this on before it works. There you go. And we're going to begin way back with your ancient ancestors' solar system. Okay? Your ancient ancestors who didn't have these telescopes and computers and everything, and only looked at the sky. And what would you notice when you look at the sky? Well, the first thing you would notice is that there's this sun in the sky, and it traverses across the sky in the course of a day, right? It goes from east to west, mostly east to mostly west, right, as we discussed in the misconceptions idea. You'll also notice that there's this big thing called the moon, which is roughly the same size as the sun, and it goes through these various phases and moves across the sky. It moves across the sky in a day, but it goes through these phases in about a month. Okay, actually 29.3 days. It goes through the various phases. You would also notice that you have stars, and these stars rotate around the sky, and they do so in about a day. Actually, they rotate around the sky in 23 hours and 56 minutes, just slightly short of a day. All right, that's the difference between a sidereal day and a solar day. All right, and that causes the stars to change positions over the course of a year. And we know that the sun is in various different constellations as it goes through the course of a year. That's why you can see Orion in the winter, and you see Scorpius in September. Okay, you can see different stars in the sky, night sky at different times, because the stars are moving slightly differently. All right? You also may notice that the sun gets higher and lower over the course of the year. This is a beautiful picture taken at the same time each day for various days throughout the year, seeing the height of the sun. All right, this is called the analemma, that the sun traces out. All right, with the summer solstice and the winter, the summer and winter solstices and an equinox identified here. And you also might notice these funny things that move around the sky in not so quite so regular patterns. These ones, which are called Venus and Mercury, which we call planets. And they have a little bit of a wandering motion to them. And you'll notice that everything seems to be rotating around the sky. And your first approximation of organizing all this would be to make a nice circular diagram with us here at the center. Earth in the center, and going by the timing that it takes things to go around. Okay, the moon is the closest because it goes around in 30 days. And then we've got Mercury, which has an 88 day. And then Venus, which is 267 days. And then the sun and Mars and Jupiter and Saturn. And those are all the things you can see with the naked eye. Okay? And that's how you might organize the solar system. And this is generally accredited to Claudius Ptolemy, because in the year 150 CE, he wrote a book that has come to known as the Almagest. Okay? It's not actually called the Almagest. It is a mathematic systematic treatise that he wrote, in which he extolled the Earth-centered solar system. Since we talked about misconceptions this morning, let me raise one big misconception. Ptolemy invented the Earth-centered solar system. Sorry, thanks for playing. Ptolemy did not invent it. Ptolemy organized and systematized the Earth-centered solar system based on ideas that had been developed over about 600 years, all the way back to Pythagoras. Okay? From 500 BCE onward, there are a whole range of ideas that got organized and put into Ptolemy's book. All right? He didn't add very much, but what he did really add was a nice way to calculate positions in the sky based upon all these ideas, and that's one of the reasons why his book became so famous and stuck for being the main treatise for over 1,500 years. Okay, because he could give you a nice way to calculate, put in these numbers, get out these numbers, and you know where to look, and you can tell where the planets will be in the sky. All right? Now, speaking of those planets, I mentioned that they were sort of wanderers. Matter of fact, planet is a Greek word for wanderer, okay? Because they don't quite follow these nice normal motions of everything else. They actually do some funky things. So this is the path of Mars against the background stars. It moves this way, but sometimes it moves back, and then sometimes moves back forward. We call this retrograde motion. All right, and in order to explain this, we couldn't use just circles. We had to use circles on top of circles. Oops, let me clear this. I was playing with this earlier. Okay, so here is the orbit of Mars in the Ptolemaic solar system. The sun is in here. Here is the equant, which is the circle that this C point moves. And Mars is here on the epicycle that moves around the equant. All right? Now if I put it in motion, you can see that this is the motion viewed from Earth at the center. You can see Mars moving through its epicycle. And I'm going to turn on a trail. Okay? So you can follow the trail of Mars. And at this point, when it gets on the inside of the epicycle, it actually appears to move backward on the sky and then moves back forward on the sky. All right? So this is how they accounted for that retrograde motion. And if I speed it up, we can see why Ptolemy became famous. All right? Because Ptolemy invented spirograph 1,800 years before the Hasbro Corporation. All right. So, equants and epicycles, it's a game of spirograph with the solar system, but it allowed you to calculate where the planets would be, and it did actually a good job. Okay? So, now we transition to where we start your parent solar system. Okay? Oops, sorry about that. So your parent solar system begins with Nicholas Copernicus, who in 1543, in his dying years, some say on his deathbed, was the first time he saw his book published on the revolutions of heavenly spheres. He actually wrote it over about a 30-year period and was a little shy about publishing it because he wasn't totally sure it would get accepted on that. And he did this. He took the Earth and Moon and the Sun and swapped positions. That's it. Okay? Very simple. Swapping positions with, of course, the philosophical argument of the much larger sun should be stationary and so forth. All right? So, misconception. Copernicus's sun-centered solar system was quickly accepted because it was much simpler and more accurate. Thank you for playing. No, Copernicus' sun-centered solar system was just as complex as Ptolemy's Earth-centered one. It still uses those epicycles, okay? Copernicus didn't get rid of the epicycles. He kept them because they were really good at predicting things. All right, they were changed in size and everything. They were still there. And actually, it provided no more accuracy in its predictions. They kept the Copernican solar system, okay? So you will find it everywhere that the myth that Copernicus came up with this and everyone said, huzzah, huzzah, it's a wonderful new sun-centered solar system. It was not accepted in 1543, okay? It took a long time for the sun-centered solar system to be accepted, all right? Next player in the story is Galileo, and in 1609 he first used a telescope for astronomy, and in 1632 he was tried by the Inquisition. Those are the two major things people remember about him. One of the misconceptions about him is that Galileo invented the telescope and was the first to use it for astronomy. Both of those postulations are wrong. He did not invent the telescope. He was one of several folks who took the spyglass that was invented probably in Holland. They have a patent application for it in Holland from 1608. Improved it so that it could be used for astronomy, and he was one of the few people who did use it for astronomy. His main claim to fame, what makes him so famous, is that he published. Okay? I talked about publish or perish in the last session. He published. Sidereus Nuncius came out in 1610 and described the moons of Jupiter, which he called the Medicean stars. It described the mountains on the moon, described several other things. Getting out and actually publishing your scientific observations was his great feat. Okay, it always goes through his Dialogos, which is what the Inquisition tried him for. Okay, and that brings up yet another misconception about Galileo. And the misconception is that Galileo proved that Copernicus' sun-centered solar system was correct, and that's why he was subject to house arrest in the Inquisition and tried by the Inquisition. Wrong. He was not. He was tried for this, but he did not prove it. He tried to prove the solar system, but his arguments were wrong. He used the tides as an argument for the sun-centered solar system, and you look at it now and you go, no, that just doesn't work out. Why would you convict him of proving something yet he did not prove? The actual route to the sun-centered solar system does not come through Galileo, although he was a strong advocate of the Copernican system. Actually, if you look back to his Dialogos, he's talking about the system of the world both due to Ptolemy and Copernicus. All right, and it is through Ptolemy, it is through Tycho Brahe and Johannes Kepler that we actually get to the sun-centered solar system. Now, Tycho Brahe was the greatest pre-telescopic observer. All right, this is a picture of him using his giant mural quadrant, where he would line up the objects, and as they passed through the north-south line, he would measure their angle above the horizon. So yes, the greatest instrument before the telescope was a giant protractor. Okay? And then his assistant was hired to work with him, Johannes Kepler, was a theorist. And when Tycho Brahe died in 1601, Kepler inherited his data, and then Kepler produced on the motions of Mars, which he calls his war with Mars, and based upon incredibly accurate observations of Tycho Brahe, he was able to deduce that you couldn't fit Mars's orbit with a circle, okay, or epicycles on top of it. Instead, it would work better if you used ellipses. And it was Kepler's idea of ellipses that really settled it, okay? So, let's take that equant motion and compare it to Kepler's motions, and I love this because, let's see, we've got the eccentricity dialed up nice and high. All right, now watch the difference between these. All right, notice that the difference between the green and the blue line is very, very small. Okay, and this is an eccentricity of 0.4, which is much larger than the one that Kepler was dealing with. Okay, but Brahe's observations were so careful, he could tell these very fine differences between them and come up with, yes, it had to be an ellipse and not that equant motion. Let's click here. All right. So the misconception here is astronomers embrace the sun-centered solar system because it is philosophically simpler. Okay, it is philosophically simpler, but we don't give a damn. Okay? What we really care about is whether we can get more accuracy. So it wasn't until Kepler produced the Rudolphine tables in 1627 or 1629 that astronomers embraced the sun-centered solar system only when it could provide better predictions. Up until Kepler, the Ptolemaic solar system produced just as good or better predictions than the Copernican solar system. But the Copernican solar system, with the addition of ellipses, finally made better predictions, and that's when astronomers embraced it. So, we're not philosophers. We are really practical, and we will go with whatever produces better predictions. Okay? If you really want to prove the solar system, you have to wait till Isaac Newton in 1687 in his Principia provide the mathematical foundations for why Kepler's observations were correct. Kepler has these three laws. All three of those laws of Kepler are observationally based. With the law of gravity, you can then mathematically prove that they should come out of the law of gravity if you have a 1 over r squared force. I will also note that this silly idea of Isaac Newton's was not also immediately accepted. It took about 75 years for Newton's ideas to be accepted too, okay? We have this idea that looking in hindsight, you should immediately accept it, but that's because we've got a couple hundred years of hindsight. Okay, at the time, the fact that you could mathematically predict things, you know, was kind of crazy, all right? And actually, Halley's comet plays a good role in proving that Isaac Newton was right. But I don't have time for that. We're going to move forward to talk about William Herschel in 1787, who discovered Uranus. And this is Herschel in his later years with his big professional telescope. But of course, when he was starting out, he wasn't a professional, he was an amateur. He didn't use this giant, wonderful telescope to discover Uranus. He actually used a 7-foot-long telescope that he made by himself, okay? You do not need to be a professional to discover things in astronomy. I guess I could put that up as another misconception, okay? Amateurs discover things all the time in astronomy, especially in terms of comets and asteroids. The first planet ever discovered was discovered by an amateur, okay? Because he was more careful. Other people had actually seen Uranus, including actually, no, it wasn't Galileo, it was Flamsteed, had recorded the position of Uranus several times, just didn't notice it. He's the one who noticed it, okay? In 1801, we have the next planet discovered, which is Ceres, by Piazzi, followed quickly by 1802, Pallas, Juno, Vesta, and then there's a gap until 1845 when we had the planet Estrella uncovered, okay? So going into the 1840s, that gives us, what, 7 plus 5, 12 planets that we had. And then the most amazing thing happened, something that proved, actually it was called the best conceivable proof of Newton's law of gravity imaginable. And it is when Van Leverrier and John Couch Adams predicted the existence of Neptune based upon variations in the orbit of Uranus. Okay? They had noticed that Uranus didn't quite follow the path that they had been predicting for it, and they couldn't explain it with any of the known objects, so they postulated that there was another unknown object that was pulling on Uranus and perturbing its orbit. They predicted where it was, and nobody would listen to them. Nobody would look for it. And when they did look for it, they did this long, methodical search in England, but Urbain Le Verrier got tired of asking the French to look for it, and they didn't look for it, so he called up the Germans. They found it the very first night. Okay? The Germans found the planet that the French and the English had predicted. You can imagine the nationalistic warfare that went over that in the scientific circles, okay? That is an incredible soap opera that I don't have time for today. All right. So, here we had at the end of the around 1850, we have the rocky planets, the 4 rocky planets in the center, and then we have the giant planets. All 8 planets are there, but we've also got these other planets in between Mars and Jupiter. We plotted 4 here: Juno, Vesta, Pallas, and Ceres. Okay, these were planets for about 50 years. And so the misconception that comes up is, you can't just demote a planet! I've heard that a lot over the last decade, as you might imagine. Actually, we have done it. We've done it. In the mid-1800s, astronomers demoted the many planets between Mars and Jupiter's to be, of course, the asteroid belt. Okay? We started discovering in the 1850s and 1860s dozens of objects in between Mars and Jupiter. Okay? And it just stopped making sense to call them planets. We knew we had a new family of objects. We called them the asteroid belt. Actually, the Astronomer Royal in 1801, when Ceres was discovered, he suggested the word asteroid for it because he didn't think it was a planet at that time. He turned out to be right 50 years later. All right, moving forward. The next thing that happened, well, actually, there's a whole bunch of things I'm skipping over here, which were mistaken discoveries and predictions and all that sort of stuff. Clyde Tombaugh in 1930 had the discovery of Pluto. This is Clyde. This is the telescope he used. This is actually how we discovered it, using what's called a blink comparator, okay? Where he had one plate here and one plate here, and he flipped a mirror in this switch to look back and forth, looking for objects that moved relative to the background stars, okay? I'll show you his discovery back then. Misconception about Pluto is that Pluto's discovery relied on mathematical predictions based on perturbations in Neptune's orbit. Matter of fact, this is what Percival Lowell did. He saw perturbations in Neptune's orbit, and he predicted the existence of Pluto. He set up Lowell Observatory to do that, to look for it. He put lots of money into the program. They hired Clyde Tombaugh, who found it. So it sounds like a great story, just like Adams and Leverrier finding Neptune, right? Wrong. Pluto's discovery relied solely on the incredible observing skill and dedication of Clyde Tombaugh. Okay? Neptune's orbit shows absolutely none of the claimed perturbations. All the money that Percival Lowell put in there was based on bad observations. Okay? He thought he saw perturbations in Neptune's orbit. You go back and look at it, there were no perturbations at the level that he thought there were there. Okay? He put tons of money into this. So, I really, really, really have to say how incredible it is that Clyde Tombaugh found Pluto in 1930. Incredible observing skill. All the credit has to go to him. Okay? I call it Percival Lowell's second greatest mistake. Of course, his first greatest mistake being the canals on Mars, which was 1896, where he thought there was evidence of civilization on Mars. All right. So, you'll see perhaps this in your textbook describing your parent solar system, and I give you permission to put a great big red X through it. Okay? As we've discussed before, they're never in alignment. These spacings are absolutely horrible here. There's a little bit of size doing here. This is not what your solar system looked like, but in your old textbook, that would have been there. Also, you would have had one chapter on the sun. You would have had one chapter on Mercury. Okay? I can tell this is Mercury because there's a hole missing of it. A lot of people say, oh, it looks like the moon. Okay? We are just now getting full surface maps of Mercury from the MESSENGER mission. All right, we have gone up until last year without a full surface map of Mercury. We now have it. I had to update this presentation so I can have one of those. Okay, we got Venus. Venus actually looks less like this. It's more creamy white and fully cloud covered. You can't get a good visible light image of Venus. I'm sorry. Most of the images of Venus in your textbooks will all be radar maps of Venus, which look nothing like what it looks like to the human eye. I try to come up with some things that are closer to the human eye view. Of course, we have Earth, the Moon, which is an honorary planet in how we do things, Mars, a chapter on Jupiter. We'll talk about the ring giant Saturn. We'll have Uranus, if your textbook was produced after the Voyager era, Neptune, and then maybe you'll get a chapter on, well, you'll talk about Pluto, okay, but they won't have much to say, so it'll be a very short chapter. By the way, if you see this image in your textbook, that's not a picture of Pluto. That is a map of Pluto based on the images. This, whoops, sorry, let's go back. Back, I said. Back. Thank you. This up here, that's the best image ever taken of Pluto from the Hubble Space Telescope. That is as fine as it can be resolved, even with Hubble. Okay, this is a map based on that. Okay, you'll have one chapter perhaps on moons, and a chapter on asteroids and comets as the detritus of the solar system. All right? And that's what you will have in your parent solar system. The sun, 9 planets, and then all this other stuff. All right? And how do we remember the solar system? How did most of us, when we came out of our solar system unit, what did we remember? We had the order of the planets, all right, which several of the people right here in front of me just said. All right, I don't know what you learned. I remember it as my very energetic mother just served us 9 pizzas. Okay? And this is fine for doing this. But if that's all you remember, you don't know squat. Okay? Because you know facts, but facts are not knowledge. Okay? Facts are requisites before you get to knowledge, but synthesizing the facts into an explanation is what makes for knowledge. Okay? Memorization doesn't give you understanding. You get these factoids, you know, Mars is rusty, dusty, and red, okay? Highlights the differences between things. You don't get any big picture or the relevance between it, okay? So how do we improve this? Well, we had this amazing era of the Voyager satellites, which turned these little dots in the sky into worlds unto themselves, okay? I think the Voyager era was the greatest transformation in our understanding of the solar system because it allowed us to do comparative planetology. What do I mean by that? We want to compare and contrast discuss the broad ideas and apply them to the planets and moons and all of these things as a group. And instead of highlighting the differences, Mars is red, Jupiter is orange, Neptune is blue, you're actually going to talk about the similarities, okay? These ones have deep gaseous atmospheres, all right? The characteristics and the events that are going on in them. Let's give you an example. Here's Hurricane Isabel, okay? Which we remember in Baltimore, all right? And because it was a problem for us in Baltimore. All right, and here it is out in the ocean. Now, you can't really get a good feel for how big it is when it's just contrasted against the ocean, but let it start to come up against the eastern United States, and you can see it goes as far south as Florida and Cuba, and as far north as Cape Cod. That's a pretty big storm, okay? That stretches out across there. All right, but let's compare that to other places in the solar system. All right, here's another storm in the solar system. It's called Jupiter's Great Red Spot. All right, this is it right here. By the way, this is one of my favorite images in all of astronomy, because you look at all the vortices going on in here, amazing artistic creations due to, vorticities and all that fun stuff. All right, this is also a storm, this is also a storm, this is a storm, this is a storm, this is a storm. Okay, let's put it into context. This is the Great Red Spot, and in comparison, you want to see Isabel? Oh, I don't want to show you Isabel, I want to show you Earth. Okay? This is the size of our entire planet, okay? Yeah, they go big on Jupiter, okay? We've got storms the size of your entire planet there, okay? All right, so maybe we're not so impressed with our own storms, okay? We can do other things. We can take a look at the state of Arizona. What's the most famous thing in the state of Arizona? The Grand Canyon. It's so big that you can see it from space. Can you guys pick it out up here? That's the Grand Canyon. You can see it from space. Let's zoom in a little bit. All right? And here you can see the Grand Canyon. I had a blast. My wife and I, just after we got married, sort of as a honeymoon after the honeymoon, we took a river rafting trip all down the Grand Canyon. It was fantastic. We did paddling through there. Unbelievable, okay? But, you know, they got canyons on other planets too, okay? Here's a canyon on Mars. It's called Valles Marineris, or Mariner Valley, all right? And it's kind of nice, but for context, you can see it from space. Matter of fact, you can see it from space when you're looking at the entire planet. Here's Valles Marineris down here, okay? All right? That's how big it is. You want to know how big it is in comparison to Arizona? Try in comparison to the whole United States. Wow. Valles Marineris would stretch from the west coast to the east coast. Okay, it's like 10 to 100 times deeper than the Grand Canyon, and 10 to 100 times wider, longer. All right, they do them big on Mars too. All right, well, let's go further. Let's take a look at volcanoes. This is Mount St. Helens. Remember Mount St. Helens in 1980? Okay, it blew its top, literally. Before, after. Before, see all this cone up here? Goodbye, after. All right, kind of cool. Literally blew its top. So we got some interesting volcanoes here on Earth. Let's go to other places. Here's a volcano. It looks very much like that Mount St. Helens. This is from the radar map of Venus. They got cool volcanoes on Venus. All right, Venus is a very, very hot surface planet. It's got volcanoes. It's not the coolest volcano in the solar system. That belongs on Mars. Have you guys heard of Olympus Mons? Mount Olympus, okay? This is the biggest volcano in the solar system. Matter of fact, you remember the state of Arizona? It's about the same size as the entire state of Arizona. Yeah, they got canyons as long as our entire country. They got volcanoes as large as an entire state. All right? And how high is it? Well, here's a comparison against Mount Everest. Mount Everest is here. This is Olympus Mons. Okay, yeah, they do them really big in terms of volcanoes on Mars. But this is not the coolest volcanic place in the solar system. If you really want incredible volcanism, you don't go to a planet, you go to the moon, Io. Okay? This is Io, and it's got a lot of acne. All right? And that acne actually is changing and bursting and erupting We're going to look at this one right here. Okay, we're going to go close. And in April 2007, we saw this. And September 2007, we saw that. Change on the moon. What is that? That's a volcanic eruption. Right? It's an eruption of sulfur dioxide from the interior of Io. Io is on a slightly elliptical orbit. It's getting gravitationally flexed by Jupiter, and it's causing incredible volcanism. But that's not the coolest. If we take a look at Io from space, we look at its nice limb, we notice it has a pimple. We zoom in on that pimple, that's a volcanic eruption off of Io. Io is small enough, its surface gravity is low enough that the volcanic eruptions can spread out to a noticeable distance from it. Okay? On Earth, our volcanic eruptions just stay within our atmosphere, which is that tiny 1/64th of our radius. Okay? This goes out to an appreciable fraction of the radius. And the coolest volcano in the entire solar system was captured by the New Horizons mission on its way out to see Pluto. All right? It's called Tavashtar. This is an animated GIF of Tavashtar. Is that cool or what? Okay, you're watching a volcano erupt on a moon of another solar system. On a moon elsewhere in our solar system. That's kind of cool, all right? So by doing this, we can do these comparisons and see how the geologic processes, how the atmospheres, how everything is similar and yet different on the various bodies of the solar system. We discussed canyons and volcanoes. We could have done craters. We could have storms, winds, seasons, weather, ice flows, magnetic fields, moons, rings, whole suite of these things. And we start to gain a better understanding of the solar system. This comparative planetology has the great message that what happens here on Earth happens elsewhere in the solar system, and therefore the solar system is understandable. It's not this strange, unimaginable place. It's an extrapolation of what we know here on Earth out to the rest of the solar system. And this gives us the pieces with which we can assemble the big picture, and that big picture I call the 21st century solar system. All right? And I'll explain this diagram in just a minute, but there are not the sun and 9 planets, 10 things in the solar system. There are, if you want to remember a number, 6 things in the solar system. The sun, the rocky planets, the asteroid belt, the giant planets, the Kuiper belt, and the Oort cloud. These last 2 you may not have heard of, but we'll go through them. All right. The point is that these are classes of similar objects in their size, their composition, their orbit shape, their orbit tilt, the number of moons, whether they have rings, all of the characteristics that we like in science to group things together to make a common understanding. All right? So let's start with the sun. The sun is the only star in our solar system. Okay? It is a category of 1. Unfortunately, we hate categories of 1 in science, but this is the gravitational and literally and figuratively the center of the solar system because it contains 99.7% of the mass or something like that of the solar system. Okay, it is the sine qua non, that without which everything else would not happen. Okay? Then outside that, we have the rocky planets. And we've got Mercury, Venus, Earth, and Mars. Notice that I plotted them, I put them up here at their relative sizes. And in roughly what the human eye would see, again, Venus, this is slightly in the ultraviolet, so you can see a little bit of something in the cloud tops. In visible light, you wouldn't see anything. And the moon is there as an honorary planet, just for comparison, because everyone knows and loves the moon. All right? What are the characteristics of these? They're mostly rock. They have relatively thin atmospheres compared to their radius. Okay? Earth's atmosphere is only 1/64th of its radius. It's 100 kilometers thick. Venus and Mars both have 100 kilometer thick atmospheres. Mercury and Moon have no atmospheres. They have few moons. Earth has 1. Mars has 2 pathetic little nothing captured asteroids that they count as moons, but they aren't respectable moons by any means. Venus, Mercury, no moons. Okay, they're all roughly the same size. Okay, they have magnetic fields for some of them. The other ones don't. Earth, with its dynamo, has the strongest of the magnetic fields. But you can get similar characteristics for them. Okay. Outside of that, we have the asteroid belt. And if you want to show your students an asteroid, you go to the supermarket and buy a potato, and then use the potato peeler to cut holes in it to create the divots due to impact, and there you've got a model of an asteroid. Your average asteroid is a potato. Okay? It's potato shaped. Now, the asteroids have one great big misconception, which has been promulgated by Hollywood. Hollywood's view of the asteroid belt is, oh my God, we're going to crash! Oh, sweet, oh my God, no, we're never going to make it! And it makes for fun stuff in a movie. It is unfortunately totally wrong. So here we've got the scientific view of the asteroid belt, and there's a heck of a lot of them, okay? Here's the orbit of Mercury, Venus, Earth, and Mars. Here's Jupiter, and in between all these things, there are hundreds of thousands of asteroids in there, okay? However, the distance across Jupiter's orbit is almost 1 billion miles, okay? So quick, do the math. You've got hundreds of thousands of asteroids spread across a 1 billion-mile orbit, okay? The average distance between objects in the asteroid belt is about 1 million miles, okay? So even if you were moving at, say, I don't know, a tenth the speed of light, okay, that's, 18,000, 19,000 kilometers a second, miles a second, right? It would still take you 60 seconds between asteroid encounters. So you'd be, oh no, turn! And you'd have to wait for an entire minute. Oh no, turn! It wouldn't make for a very exciting Michael Bay film, would it? Michael Bay would be terribly bored by it because he wants to do something 3 times a second. All right, so no, you could fly across the asteroid belt. Most times if you fly across the asteroid belt, you would never even know you're in the asteroid belt. You have to work really hard. Our spacecraft have to work really hard to actually find an asteroid and to do an encounter by an asteroid, okay? So, the asteroids, what are their characteristics? Well, they're all pretty small. They're mostly ice. They're mostly rock. They do have some ice. Some of them have some ice. They tend to have more elongated orbits. They tend to have more tilted orbits, and they're a wide range of sizes in orbits. And they're mostly between Mars and Jupiter. You can see there are some that come inside. You get the Trojan asteroids, which are based around Jupiter's gravitationally stable points. And you have some that fly out here, which are the centaurs that are amongst the outer planets. Okay? Next group is the giant planets and Earth, here for comparison. All right, Jupiter, Saturn, Uranus, and Neptune. Again, roughly human eye colors for them, comparative sizes so that you can make a comparison. And again, you can see Earth is about the size of the great red spot. All right? Characteristics of these, they all have deep atmospheres. You can call them thick, deep atmospheres, in that the atmosphere of Jupiter goes down about 1/3 of the way into the planet. Okay? Atmosphere of Saturn goes a little bit further than that. Uranus and Neptune, deep, thick atmospheres in terms of the depth of their atmospheres. They all have rings, even though Saturn is the only one with the bright rings, as we learned this morning. All of the other ones do have rings. They're small and thin and dark, and some of them very gossamer. Jupiter's rings are actually micron-sized particles for the most part. They all have lots of moons, okay? If you learned in the previous session that 2, 4, 7, and 12 or something like that had lots of moons. Well, these are those, okay? Like 60 moons for these guys and 10 to 20 moons for these guys. They all have magnetic fields, relatively strong magnetic fields. Jupiter is especially strong, all right? Turbulent atmospheres, and so on and so forth. We have characteristics of the same. Now, we get to the 2 pieces of the solar system you might not have heard of. We'll talk about the Kuiper Belt. All right, this is a plot of Jupiter, Saturn, Uranus, and Neptune. Those orbits there. You can see the Trojan asteroids and the centaurs that I mentioned earlier. Outside of the Kuiper Belt, we've got thousands of, over 1,000 new objects, of which only one was known in 1990. Okay? All of the objects in red and white out here have been discovered since 1990. This is the new region of the solar system that has been discovered in your lifetime. Kind of cool. You thought we knew everything about the solar system? Wrong. The Kuiper Belt. What are these objects? Well, this is an artist's view of the object Quaoar. And no, I'm not making that up. My friend, who I went to graduate school, Mike Brown, named this object Quaoar after the Native American goddess of the Inuit tribe of Southern California. Something like that. I can't always remember the derivation. And he's got a sense of humor, okay? Mike is a fun guy, I'd say. All right, and what is it? It's a big, giant ice ball. Okay, you can see there the artist drew some craters on it. It's big enough to be roughly spherical. It's got craters on it from impacts and stuff, but it's mostly ice. It resembles a lot of the moons of the outer solar system. Okay, big, giant ice balls. And let me ask you, if I kicked one of these ice balls out of its orbit and it came in past the sun, what would happen? It would melt. And what happens when ice balls in the solar system melt? That stuff that melts off of them gets pushed back and they become comets. This is what the Kuiper Belt is. This is why we knew the Kuiper Belt had to exist. It is the repository for the short period comets. Okay? Comet Halley has an orbit of 76 years. All right? It will go past the sun every 76 years. Each time it goes past the sun, it will lose a small percentage of its mass. All right? Say it orbits, once every 100 years and it loses, a tenth of a percent. In less than 10 million or 100 million years, poof, that comet's gone. How old is the solar system? 4.5 billion years. If you lose all your short period comets in 100 million years, where are you going to get new ones? From the Kuiper Belt, okay? The objects in the Kuiper Belt are the repository for what will become short period comets by first migrating to become centaurs and then moving in, getting kicked around by the giant planets. Generally, Neptune moves the orbits, they move in, and they end up getting their orbits not circularized, but moved into a short period orbit that comes past the sun, and that's where you get your short period comets from. Okay? That's what the Kuiper Belt is. Now, if there are short period comets, there must be long period comets. Thank you. I love it when an audience follows along. There must be long period comets, and where do they live? Well, we have postulated the existence of the Oort cloud, which billions of icy minor planets, or as I like to think of them, comet nuclei that haven't gotten close enough to sprout a tail. All right? And we consider it roughly spherical out to 50,000 AU. 50,000 AU, how big is that, Frank? Oh, I'm glad you asked. Earth is 1 AU away from the sun. Okay, so 50,000 is 50,000 times farther than Earth. Okay, Neptune, the most distant planet, is 30 AU. So this is up to 1,000 times farther than the most distant planet. Okay, matter of fact, we had to use a logarithmic scale here to show this diagram. The inner Oort cloud is roughly confined to the disk. The outer Oort cloud is roughly spherical. Okay, it is postulated because it explains the long period comets. Let me show you what I mean by that. All right, so this is sort of an inverted graph in terms of 1 over the semi-major axis of a comet. So things on the left side have very long orbits. Things on the right side have very short orbits, okay? Short period comets, we put an arbitrary cutoff at 200 years. It peaks around 7 years, okay? A lot of comets actually intermingle with the asteroid belt in the short period comets. The long period comets, they peak around a period of infinity. Okay, that's just, of course, measurement error because we only see them once, and how can we can't measure them coming back for that. So, they have essentially 1 over the semi-major axis being 0, which gives it. But you can see there are a lot more of these long period comets than there are these short period comets, which is why we believe the Oort cloud to exist. Unfortunately, 50,000 AU is so far out there we haven't been able to see any. Except maybe we have seen one object, Sedna, okay? And this is the best image ever taken of it from Hubble, the high-resolution camera, seeing it. And Sedna's orbit goes from 76 to 840 AU. This is the Kuiper Belt here in blue and red. This is Sedna's orbit, all right? And it's a puzzling object, okay? It's got a very red color that we can't quite explain. Is it the outer Kuiper Belt? Is it an inner Oort cloud? Or would you just want to call it a planet at 70 AU? I mean, I'm sorry, Sedna is just the way that we had Pluto in 1930. We know as much about Sedna as we knew about Pluto in 1930, and it got planetary status. So why doesn't Sedna have planetary status? Because we've learned a few things since then. All right, so this is the families of the solar system. We get the classification, we get the structure, and we get clues to the solar system formation and evolution. And that comes up in this diagram. First of all, that we presume we form from a spinning disk, and within that spinning disk we start to accrete planets, and we form planets, and those planets accrete, and the stuff gets blown out of the solar system, so we get planets around them. All right, that gives us our nice circular diagram. But also, if you've got a hot sun in the center, you can't form ices next to a hot sun. So your ices in the Kuiper Belt and the Oort cloud are as far away as possible. Whereas rock can take the heat. We have rock in the rocky planets in the asteroid belt in here. We call this a volatility gradient, okay? The stuff that can stand the heat stays in the kitchen, though that doesn't, gets out of the kitchen, okay? It doesn't form in the kitchen. Ice towards the outside, less volatile material toward the inside, all right? And that helps you understand the structure and formation of the solar system. So these families in the solar system are not just, cute little things to memorize. They actually help you understand the structure. And this is how I believe the solar system should be taught, okay, in understanding families, because it gives you insight into the structure and the evolution of the solar system. But what are we going to do about a mnemonic? I mean, come on. All right, we've got all these things: Sun, Mercury, Venus, Earth, Mars, asteroid belt, Jupiter, Saturn, Uranus, Neptune, Kuiper belt, Oort cloud. Who's going to remember all those? Well, taking it as a challenge, I put my tongue firmly in cheek and came up with: some may view elaborate mnemonics as boring, just some useless, nonsensical knowledge, but others cheer. Now, I know that was tongue in cheek and that was done just to sort of put things, but you could make a commentary on the situation and say that science may view established models as basic justified standards until new knowledge bears out changes. And I know you want your very energetic mother back, don't you? Okay, so for the third one we have, sometimes my very energetic mother also boils jumbo shrimp, whoops, sorry, using 9 kettles bubbling over coals, and that's your new solar system, okay? Alright, but there's still an inevitable question that comes up, and every member to the third graders with the tears in their eyes, they go, why is Pluto no longer a planet? It's my favorite! Alright, so let's talk about it. Okay, I was at the Hayden Planetarium. Neil Tyson, Steve Soder, and I kicked Pluto out of the solar system in 2000 because we put it in the Kuiper Belt in our exhibits. Why? Because our exhibits were going to stand for 20 years, and we knew that eventually astronomers would get around to declassifying Pluto as a planet, and we didn't want to be behind the curve and have to update our exhibits. We're cheap, right? All right, so we got a lot of guff for it, but in 2006 we were unvilified, although we're still vilified a little bit. Okay, so this is planet Pluto as it was discovered in 1930. On January 23rd it was here, and on January 29th it was here. Obvious, right? It's a planet. This shows you just how damn good Clyde Tombaugh was, okay? And being able to find the needle in the haystack of this. And he did this every night for 3 years, looking for Pluto and other objects. All right, so it's tiny on plate, but doesn't mean it's tiny. Okay, because, Pluto was supposed to be this big planet. It was predicted by Percival Lowell to be 7 to 10 times the mass of Earth. Okay, and if Earth's a planet, well, if it's 7 to 10 times the mass of Earth, it should be. But as I've shown you, even with the Hubble Space Telescope, our best pictures are pretty darn ratty. We don't have much. We will get new ones in 2015. All right, but then we had the hunchback of the outer solar system. Here's Pluto. Here's Pluto as a hunchback. We astronomers say, that means it has a moon, right? Obvious. Well, the hunchback it has to be something. If the hunchback goes away, that shows you there must be a moon orbiting around it. Weren't able to see it clearly until Hubble went up, and we got some beautiful pictures of Pluto and its moon, Charon, discovered in 1978 by James Christie at the U.S. Naval Observatory. With Pluto's orbiting around it, with Charon orbiting around it, you're able to get a good mass for it. Lowell's planet was like 7 times Earth. In the 1940s, we couldn't realize that it was at most one time Earth mass. By 1980, we had it down to, well, maybe it's a 10th Earth mass. With Charon, we were able to recognize it was 0.002 times Earth. So an astronomer came up with this plot here. Here are the masses of Pluto, and he had a firm prediction by 1990, Pluto would eventually disappear. It did not disappear because in 85 we were able to get it, but that's kind of cute in terms of the shrinking of the planet. All right? In comparative sizes, here are the giant planets, here are the rocky planets and the moon, and here's Pluto and Charon down there. So it doesn't fit in. It's not a giant. It's not a giant planet. It's not a rocky planet. All right. Matter of fact, Pluto is smaller than 7 moons of the solar system. Okay. Ganymede, Titan, Callisto, Io, our moon, Europa, and Triton are all larger than Pluto. So where does it fit in? It became in the 1980s the black sheep of the solar system. The ugly duckling that nobody wanted to play with. Okay. Out at the edge of the solar system. Frozen wasteland, hey, Pluto, we don't want to play with you. If you look at it in terms of masses, you can see the giant planets, you can see the rocky planets, you can see these moons, you can see Pluto, and all this other stuff leading up to it, okay? What the heck is all this other stuff? Well, some of them are moons, those in blue, but others are in the Kuiper Belt. In 1992, Dave Jewett and Jane Liu found an object they called QB1. Okay, and here is the background stars, and here is the motion of that object. Now we're doing the blink comparator that Clyde Tombaugh did, but we've got computers to help us. We don't have to stare at them. We get the computers to stare at them, blink through them, find things that are moving, then alert us, and then we have to visually look at things. Well, you get about 1 in 100 good things out of that, but you don't only have to look at 1 in 100. You only have to look at 100 plates instead of looking at 10,000 plates or whatever Clyde Tombaugh did. This was at a distance of 42 AU. The average distance of Pluto is 40 AU. All right? This was hailed as the first object discovered in the Kuiper Belt. You might call it the third one because Pluto and Charon were already known and they're already out there. All right? Once we know they're out there, we know how to discover them, we go and find more. Here's one from Hubble's observation. Here it was at 7 in the morning. Here it is at 7 in the evening. Okay? We now know of over 1,000 objects out in this region of the solar system. Okay? You've got more stuff there. All right? And you still have to question, isn't Pluto special in some way? All right? No, it's not. Let me show you why I believe that. Here's Pluto and Charon's orbit versus a Kuiper Belt object called 2004 DW. One is in red, one is in blue. Can anybody besides the astronomers in the room tell me which is which? You can't because the orbits are very similar. The only way I as an astronomer know is that I know that Pluto has just crossed the orbit of Neptune, so it must be this one. This one is too far out for Pluto for it to be Pluto. Otherwise, the orbits are extremely similar. They're slightly elliptical, they're slightly tilted, okay? Pluto's orbit is definitely within the Kuiper Belt. Here's that orbit overlaid on top of the Kuiper Belt. You can't tell me that that orbit isn't within that region of the solar system, okay? But it has a moon, okay? I mean, come on. Kuiper Belt objects don't have moons. Only planets have moons. Sorry, wrong. First of all, is it really a moon? Because the gravitational center of Pluto and Charon is not within the center of Pluto. It's actually outside the system, and generally we would refer to that as a double object. So there's a question of whether it really is a moon, but it's actually got more than one moon because in 2006 we discovered Nix and Hydra, second and third moons of Pluto, and in 2010 and 2012 we discovered P4 and P5. So it's now got 5 moons, okay? That's got to make it special. No, it doesn't. Presence of a moon does not a planet make. Here is 1998 WW31. It has a moon. Matter of fact, of the 4 largest Kuiper Belt objects, Pluto, Makemake, Haumea, and Eris, 3 of them have moons. Only Makemake doesn't have moons. We have asteroids that have moons, okay? I'm sorry, presence of a moon does not bestow planethood on it. Okay, its size, Pluto and Eris are approximately the exact same size. At first, Eris was thought to be 10% bigger. We've now found that Pluto and Eris are pretty much the exact same size. It's not the king of the Kuiper Belt, or the queen, whichever gender you want to give Pluto. All right, and it has several other objects that are of the same size. Okay, it's not like these 2 are much bigger than all the rest. We got a nice distribution of sizes. So its orbit is similar, its size is similar, companions are common, its composition is similar. If it walks like a duck and it quacks like a duck, what are you going to call it? It's a duck! All right, we've got ducks out at the edge of the solar system. We call them Kuiper Belt objects, and Pluto has finally found its family. Okay? As the black sheep, as the ugly duckling of the solar system. I actually did this in my daughter's kindergarten class. They loved it. The ugly duckling that turned into a swan, and one of the largest objects in the Kuiper Belt. It's found its family. It's so happy. The kids love it. All right. So, what is the IAU definition of a planet? Well, in August 2006, what kicks Pluto out of its planethood is that for the first time ever we define a planet that it orbits the sun. It has an upper mass limit of not massive enough to produce fusion, okay? If you produce fusion, you're a star or you're a brown dwarf. Deuterium fusion occurs at about 15 times Jupiter's mass. That's the lower limit of a brown dwarf. Anything below that is a planet. But there's also a lower mass limit, massive enough for gravity to make it spherical. And that puts it at roughly 500 miles in diameter, depending upon your composition, okay? Icy things can be spherical, different radii than rocky things, etc. And number 4 is that it must dominate its orbit, okay? That it must be the majority shareholder in its region of the solar system. And then they define these things called dwarf planets that meet categories 1, 2, criteria 1, 2, and 3, but not 4, okay? In my opinion, dwarf planets is a totally useless and stupid definition, okay? As I said, I preface that's my opinion, okay? Other people like our solar system expert may disagree with me, but I don't see any reason for a dwarf planet because if Ceres is a dwarf planet and Pluto is a dwarf planet, what do they have in common? Size. Do they have location in common? No, okay? Composition in common? No. Are they formed in the same way? Kind of, sort of, but they're in different regions of the solar system, and I just find trying to create a category based solely on size kind of, annoying to me, okay? It doesn't teach you anything about the solar system. I still want to go with this, all right? And there have been others who have been trying to use more mathematical definitions. If you look up the links, we've got, if you look at the mass and the mass of the object versus the mass of the stuff in its region, okay, this is a way of showing that these guys up here dominate their region of the solar system. These guys down here don't dominate. So 4 dwarf planets that wannabes, Ceres, Pallas, Pluto, and Eris, are demonstrably below the line where they might dominate the mass in their orbit, around their orbit in the solar system. Okay? A whole lot of people have gone through there. But the real kicker is, what about other planetary systems? Because the very first definition first thing in an orbital planet was that it orbits the sun. And our solar system alone is just a category of 1. We have discovered planets. We're now discovering planets around other solar systems. Almost as many planets as we have Kuiper Belt objects, okay? We have seen these disks of material around planets, disks in which planets will form. We have, by seeing the wobble in a planet, detected gravitationally the pull of a planet orbiting around that star. We've done hundreds of planets like that. We've actually, because planets sometimes pass in front of their stars, detected a dip in the light that tells us a planet is there, and then from that we can actually get the size of those planets. We have actually seen planets, the light from planets. This is HR 8799, all of the light from the star. We carefully model the point spread function. We subtract off that light, and what do we see? Dot 1, 2, and 3. These is actually the infrared light from 3 planets. We don't have to just infer that they're there. We can actually see several planets now. And we can go even further, because some of those planets that cross in front of their star, the light will pass through their atmosphere. We take a picture during transit and off transit. We can subtract off the light of the star, and we can get the light of that planet's atmosphere and deduce the chemical composition of their atmosphere. We have detected molecules in other planets' atmospheres. We are in an incredible era where we're learning about planets around other stars. And what have we found? We found Jupiter-mass planets in Mercury-sized orbits. They have these highly elliptical orbits. There are multiple Jupiter-sized planets orbiting around it. We've got planets around pulsars. We have found all sorts of varieties of planetary systems, and how many of them look like our own solar system? So far, not any. Okay? Now, I'm not saying we won't. There are some that are slightly similar. We can say, oh, that's sort of like it. But any that look just like ours, and that beautiful model that we had developed for creating our solar system, we haven't got it yet. We have said that planet systems form in a predictable fashion from a spinning circular disk, but that's not necessarily true, okay? It is a lot more randomness in the material. We know that planets migrate. They can get on these giant elliptical orbits, okay? So this beautiful model that we have here applies to our solar system. It gives us a great view of our solar system, but there is so much, there's supposed to be so much more to discover. Is our solar system the oddball? We need to generalize our formation and evolution scenarios, and there's great implications for life in the universe. Because if you've got a Jupiter-sized planet on a huge elliptical orbit, how are you going to get a nice stable orbit for an Earth to form and have life develop, which takes billions of years, right? And requires a relatively stable orbit, okay? So we're in a new era of solar system study, not only in our own solar system, but for solar systems across the universe. It is definitely not your parents' solar system. Thank you.
Wow, how do you follow up something like that? Well, I've got something for you today. Before we leave today, remember this morning when we were looking at this pre-workshop activity? Did you get that